All right, so over here on the board, during the quiz, I wrote out what this means. So we did this long division problem here of polynomials, and this means we can write the original thing that we're dividing into, the cubic, as the thing we divided by g of x. This is the f of x, this is the g of x. The g of x divided by the quotient plus the remainder. And this ends up being most significant if the remainder is 0, because if the remainder is 0, that's going to mean that term doesn't need to be written, and it means this polynomial is divisible by both of these. These are both factors of the original thing we both divided. Now they don't in this example because there's a non-zero remainder there. By the way, we could have done this in, say, well, with these original coefficients that we're looking at here, we could have done this in, say, z7x and done the division mod 7, for example. Although with minus 7, you'd think of that as really 0. Maybe it would be better to think of that as z8. That's not a field, though. z11, maybe. And think of x minus 7 then maybe as x plus 4. Negative 7 equals positive 4 mod 11. All right, I got to go pretty fast through the next few slides if we're going to get done in time and get to the final example that relates this back to chapter 14. So hang on here. You probably, maybe it's best not to write these down except maybe just the names of the theorems. Okay, this is a definition. Don't write this down for the moment, but think about it. It should make sense. The deviant integral domain, it's related to what I just said. If f of x and g of x are in the polynomial ring with coefficients in D, we say g of x divides f of x, and we write the usual kind of symbolism with the divide symbol there. If what? If f of x is g of x times something. If there's an h of x, so that f of x is g of x times h of x. G divides f. Better, I should say g of x divides f of x. We also say g of x is a factor of f of x in this situation. This should make sense. When f is a field, you might wonder why we don't do this for an integral domain as well. We theoretically could. But again, this is one of those situations where it's going to be simpler to consider the case where the coefficients are from a field, because the theory is going to all work out better, more nicely. We say a is a 0 or root of f of x if f of a is 0, like always. This means what you think it means. Plug in a in place of x. So there we are thinking of the polynomial as more than just a symbolic thing. We are saying, okay, we can replace x with some ring element a and do some actual ring computations. If f of x, well, okay, if f of x has coefficients that I'll label b's here instead of a's to distinguish them here. By this is what you would think it means go ahead and replace all the x's with a's and then do the ring computations. So a to the n power really does mean a to the n power in that ring, the coefficient ring, which in this case is a field actually. Multiplied by bn in the field. Add this thing, etc. Okay. And it is a field, so you can do those actual operations in any order. And even if it were an integral domain, you could do them in any order as well. It's going to be, well, it's commutative with respect to addition always. You could switch these around because it would be commutative with respect to multiplication as well. We say a is a 0 of multiplicity k if x minus a to the k is a factor of f of x, but x minus a to the k plus 1 is not. Which actually begs a little bit of a question. Does a 0 of multiplicity 1 correspond to the idea of a 0 here? That's technically something that should be thought about and maybe proved. And we do prove it. The book proves it, related to facts on the next slide. Okay, I'm going to go to the next slide if you see a few people writing, but find this stuff in chapter 16. Corollary 1, the remainder theorem. Don't write this down, just write the name. And then just listen. Let F be a field. Let A be an element of the field. Let f of x be a polynomial in the polynomial ring with coefficients in f. Then f of a is the remainder when dividing f of x by x minus a. Well, maybe I shouldn't erase this. 578 here, the remainder that we got when we did this division. The remainder that we got, we divided by, what was it, x minus 7. So you see there. That is also, that 578 by this theorem, this corollary, is also the value of this polynomial when you plug in 7. That's what this is saying. Which shouldn't be surprising if you imagine plugging in 7 right here. If you plug in 7 right there, you get 7 minus 7 is 0. 0 times this is 0 plus 578. It's easier to plug in 7 into the right side than it is to the left side. But you're going to get the same answer either way, and you are going to get 578, the remainder that we got. Proving this corollary follows very trivially from the division algorithm. You can argue the same kind of way in general from the equation of the division algorithm. When you replace x with a, which is 7 in this case, right here, this becomes 0. And makes the proof of this pretty easy. But it's a fact worth remembering. Corollary 2 is called the factor theorem. You're a little bit more used to the factor theorem, I think. Let f be a field, let a be a field element, let f of x be a polynomial in the polynomial ring with coefficients in f. Again, this is not a field. Then a is a 0 of f of x if and only if x minus a is a factor. And that's now jiving with the two ideas on the previous slide. The 0 and the 0 multiplicity k. When k is 1, those do match because of this corollary. This is something you actually know, so to speak, already. You got a 0 of a polynomial. You know you can factor it as x minus that 0 times some other polynomial. You already knew this. That's when you're going to get a remainder of 0 when you do the division, full-on division. Related theorem, which is something you already quote-unquote know as well, though not in as general a form as this. A polynomial of degree n over a field has at most n zeros counting multiplicity. You already know this when the field is the reals or the complex numbers. You already knew this. Should have known this at least. But it's true for an arbitrary field, even a finite field. That's your field of coefficients. Slide 4 about the division algorithm. Back to ideals. We haven't talked about ideals today. And we just defined it on Monday. Let f be, so this is something new, okay? This is not so easy to understand. If you want to write the page where you'll find this, it's page 283. It's really, okay, yeah. Excuse me, it is labeled as the theorem, page 283. Let f be a field, so this is our coefficient ring, which is a field here. Let I, that's an I there, be a non-zero ideal, non-trivial ideal, I could have said, in a polynomial ring. What is an ideal again? Ideals are subrings with an extra property. They are super closed, I call it. Actually, I was thinking yesterday as I was making the key, it also would make sense to call them super absorbent. And that sounds funnier even. They're super absorbent, right? You multiply an ideal element by a ring element on either side. It doesn't have to be a commutative ring. It'll get sucked into the ideal. It'll be in the ideal. They're super closed. Super absorbent. Then, what can you say? G of x is an element of the polynomial ring. The ideal is the same as the ideal generated by G of x, the principal ideal generated by G of x, I should say. If and only if G of x is a non-zero polynomial of minimum degree in I. What is the principal ideal generated by an element again? We typically thought about this. Okay, you can define this for an arbitrary ring. When I write that with group theory, that's the cyclic subgroup generated by A. It's all the powers of A. With ring theory, it's something different. Though in the example where the ring is Z, it ends up being the same set. It's the set of all multiples like this, where R varies over the entire ring. It is a commutative ring. R is a commutative ring. Here, in order for this to be a full two-sided ideal, there is a concept where this can be a one-sided ideal when the ring is not commutative. But we're only doing two-sided ideals. Set of all multiples of A, where the multiple, the coefficient, so to speak, the scalar, so to speak, is an arbitrary ring element. That's an ideal. It's called a principal ideal generated by this element A. The ideal we're talking about here is going to equal a principal ideal for a given polynomial G of x, if and only if G of x is in I, and it's also got the property that it's non-zero and it's of minimum degree. There are no polynomials in I that have smaller degree. And here's a good reason to say the degree of the zero polynomial is undefined. Because then you have to modify what you're saying here. You have to say a minimum degree except for the zero polynomial. There's no polynomial in I of smaller degree. The zero polynomial is in I because it's a subring. Ideals are subrings, but the zero polynomial has a degree that's undefined. And this is a good reason for that. Note, when f is a field, essentially because of this theorem, f of x will be a so-called principal ideal domain, PID. What is a principal ideal domain? It's an integral domain in which every ideal is a principal ideal generated by some element. A principal ideal domain is an analog in ring theory of cyclic groups in group theory. They're relatively simple rings, just like cyclic groups are relatively simple groups. By the word relatively simple, I mean not the same thing as the idea of a simple group that I talked about briefly last week. That could be complicated. An advanced topic in group theory where they had hundreds of mathematicians who were creating thousands of papers, thousands of pages of papers on classifying simple groups. It's not the same thing. By simple, cyclic groups being simple, I mean they are easy to understand. Said the idea of an irreducible polynomial is similar to the idea of a prime number. Let f be a field, a non-constant polynomial in this polynomial ring with coefficients in the field is said to be irreducible over that field. I can't stress enough the importance of putting over the field there as well. Don't just say irreducible. Say irreducible over f. That's super important. if f of x cannot be expressed as a product of two polynomials of lower degree in the polynomial ring. If not, in the opposite case, f of x is said to be reducible over f, if you can write it as a product of two polynomials of lower degree. This is analogous to prime numbers. This generalizes the concept of a prime number. Prime number, positive integer, bigger than 1 actually, that cannot be expressed as a product of two things except by 1 in itself. Two smaller positive integers except you can only factor it as 1 times itself. Here we're talking about saying if it's irreducible, you cannot express it as a product of two things of lower degree. This definition only works if the polynomial ring is over a field. There is a more general definition over an integral domain that's harder to understand than this. And we will get there, but not today. If you read about it, you'll see it in the book. A harder definition for what it means to be irreducible over an integral domain. Over a field that's simple. A quick theorem worth knowing for the example we're going to look at here in the last few minutes is called the reducibility test for degrees 2 and 3. Let f be a field, let f of x be a polynomial with coefficients in the field, and suppose the degree of f of x is 2 or 3. Then f of x is reducible, not irreducible, reducible over f. You can write it as a product of two polynomials in lower degree, if and only if f of x has a 0 in the field. All right, what are the examples we're about to look at here in the last 7-8 minutes of class? We're going to consider a single polynomial f of x equals x squared plus 1, and we're going to consider it as an element of two different rings. We could think of this as an element of this ring if we want, or of this ring, or plenty of other rings, okay? But I'm going to think about those two things. And I'm going to ask myself, is this polynomial, which has degree 2, is it reducible or not? It's an if and only if, so you can actually use this theorem to prove irreducibility as well. If it does not have a 0, it would be irreducible. As a polynomial in Z3x, is it irreducible or reducible? As a polynomial in Z2x, same question, is it irreducible or reducible over that given field? These two things are fields, since 2 and 3 are prime. Well, that reducibility test should help us figure it out. Over Z2, does it have a 0? You only have two things to check, f of 0 and f of 1. F of 0 is 1, not 0. F of 1 is 1 squared plus 1. 1 plus 1 is 0. It does have a 0. It is reducible over Z2. Therefore, f of x is reducible over Z2. You might wonder, how can it be factored then as the product of two lower degree polynomials? The answer is actually x plus 1 quantity squared. We're doing mod 2 arithmetic. That's the same as 0 mod 2. X squared plus 1 can be factored like that. Here's an equation that many students, if you're going to be a teacher, many students think is true even in R. They think x plus 1 quantity squared is that. And they're wrong in R, but in Z2 it's right. So if you're grading their paper, you can say, oh, you were right in Z2, but you're wrong in R. How about over Z3? There's three things to check. f of 0, f of 1, and f of 2. F of 0 is 1, still not 0. F of 1 is 1 squared plus 1 mod 3 now is 2, not 0. F of 2 is 2 squared plus 1, 4 plus 1 is 5, is mod 3 is 2, not 0. This same polynomial has no zeros in Z3. Therefore, f of x by that test is irreducible over Z3. And that is actually related, this is the final thing to emphasize today, that is actually related to factor rings and maximal ideals and prime ideals. We don't have time to do that. Maybe we'll have time to do a quick example calculation. Let A be the principal ideal generated by f of x in both situations. Compare and contrast these two different factor rings. Okay, there's a theorem we're going to come back to here. Don't write this down, just look and think. Let f be a field, p of x is a polynomial in f of x. Got coefficients in the field. The ideal is maximal, a maximal ideal, in this factor, in this ring here, if and only if the polynomial is irreducible over f. Corollary, this, when p of x is irreducible, this is going to be a field. This factor ring is going to be a field. And there's also a corollary that's a generalization of Euclid's lemma. Let's try to do a quick calculation. Here. Got a few minutes still. This was irreducible over Z3. So by the theorem I just showed you that you didn't really have much time to look at, if I let, in that situation, A be the ideal generated by x squared plus 1, this is maximal, a maximal ideal in that polynomial ring. Therefore, the factor ring, quotient ring, if you like, is a field by that theorem. Because A is maximal. Chapter 14, what we talked about on Monday. Lecture B. Should have read about that as well. Wrestled with. All right, what's an example? So every non-zero element should be a unit. What, for example, would be the multiplicative inverse of, say, x plus a? In here. And does it, is it non-zero, first of all, as well? Well, it is non-zero. X plus a does not equal a in the factor ring, since x is not in a, because a is the principal ideal generated by x squared plus 1, which is all polynomial multiples of x squared plus 1. There's no way you're going to multiply this by something and get x. Is that obvious? I'm not sure it's completely obvious, but just trust me on that, because you know, what if the modular arithmetic makes a bunch of things cancel to 0? I haven't proved that, but let's just take that as something that's true. So this is non-zero, so this should have an inverse. What will it be? Well, theoretically, you might say it could be some arbitrary polynomial as the coset representative plus a, but in fact, it turns out, because this is quadratic here, it turns out you can get away with a linear polynomial here as a coset representative. I'm not explaining why. The book's examples get into why in chapter 14, the one they said to struggle with. the difficult ones. Can I choose little a and little b to make this the multiplicative identity, 1 plus a? Let's see if we can. Go ahead and do the coset multiplication. You're going to get ax squared plus bx. All right, this is where it gets a little tricky. Since I'm modding by a, which is this principal ideal, x squared plus 1 plus a does equal 0 plus a. That is the 0, because x squared plus 1 is an a. And effectively, that can also be written as x squared plus a equals negative 1 plus a. So x squared can be replaced by negative 1 in the factor ring. Give me a second here. And I can replace this then by negative a. And I can write negative bx plus a equal minus little a plus capital A equals 1 plus a. If that's going to be true, I should take b to be 0 and negative a to be 1. I'm doing mod 3 arithmetic. That means a itself is 2. The additive inverse of 1 in Z3. So it should be the case that the multiplicative inverse of x plus a here is 2x plus a. And you can do a quick calculation to check that. Yeah, because you're going to get, when you multiply those, you get 2x squared plus a, replace the x squared with a negative 1, negative 2 plus a, but then do mod 3 arithmetic, this is the same as 1 plus a. I know it was fast and challenging, but that's the most important kind of thing to be working on, I think. Okay, see you Friday.